Welcome to this scientific lecture on liquid-liquid interfacial engineering for droplet microfluidics. This is a fascinating field that combines physics, chemistry, and engineering to manipulate tiny droplets at the microscale. Today we're going to explore how we can control the interface between two immiscible liquids to create, manipulate, and utilize microscopic droplets in microfluidic devices. Let me start with a fundamental question. What does immiscible mean? Immiscible liquids are liquids that do not mix with each other due to differences in their molecular structures and interactions. The classic example is oil and water. Here we see two immiscible phases separated by an interface. Water molecules on the left, oil molecules on the right, and the sharp boundary between them is the liquid-liquid interface. This brings us to another question. Why do these liquids refuse to mix? Water molecules are polar and form strong hydrogen bonds with each other. They have partial positive and negative charges. Oil molecules are non-polar hydrocarbons with only weak van der Waals interactions. They have no significant charge separation. For these liquids to mix, we would have to break the favorable hydrogen bonds in water and replace them with much weaker oil-water interactions. This is thermodynamically unfavorable. Now let's discuss one of the most important concepts: interfacial tension. Interfacial tension is defined as the force per unit length acting at the interface between two immiscible liquids. It's measured in units of millinewtons per meter. Mathematically, gamma equals force F divided by length L. Molecules at the interface have fewer favorable interactions than those in the bulk, giving them higher free energy. The system naturally tries to minimize this interfacial area. Here's a molecular view. Molecules at the interface experience unbalanced forces, pulling them toward their respective bulk phases, creating interfacial tension. Let me give you some typical values to build intuition. The water-air interface has an interfacial tension of about 72 millinewtons per meter at room temperature. For water and hexane, a common oil, the interfacial tension is around 51 millinewtons per meter. Water and fluorinated oils, commonly used in microfluidics, have interfacial tensions around 50 millinewtons per meter. Now let's connect this to droplet microfluidics. What exactly is droplet microfluidics? Droplet microfluidics is a technology where we create, manipulate, and analyze tiny droplets, typically in the picoliter to nanoliter range, within microfluidic channels. Each droplet acts as an isolated microreactor, allowing us to perform thousands or millions of independent experiments simultaneously. Here's a schematic of droplet generation. Aqueous phase enters from the side, oil flows continuously, and at the junction, discrete water droplets form and flow downstream in the oil carrier phase. You might ask, why is this technology so powerful? First, we achieve extremely high throughput. We can generate thousands of droplets per second, each requiring only picoliters of sample. Second, each droplet is completely isolated, preventing cross-contamination between experiments. Third, we have exquisite control over droplet size, composition, and generation frequency by adjusting flow rates and channel geometry. Now we arrive at the central theme. How do we engineer these interfaces? The answer is surfactants. A surfactant, or surface active agent, is a molecule with both hydrophilic and hydrophobic parts. It's amphiphilic. A surfactant molecule has a hydrophilic head that loves water and a hydrophobic tail that avoids water. This dual nature allows it to sit at interfaces. Surfactants spontaneously adsorb at the liquid-liquid interface, with their heads in the aqueous phase and tails in the oil phase. By occupying the interface, surfactants shield the unfavorable interactions between oil and water, dramatically reducing interfacial tension. The interfacial tension with surfactant is much less than without surfactant. This can drop from 50 millinewtons per meter to just a few millinewtons per meter. Let me show you how surfactant molecules organize at the interface. Here's a detailed view. Surfactant molecules form a densely packed monolayer at the interface. The red heads point into the water, the blue tails extend into the oil. An important concept is the critical micelle concentration, or CMC. At low concentrations below the CMC, surfactant molecules exist as individual monomers distributed in the solution. Above the CMC, surfactants aggregate into structures called micelles. In water, Tails cluster in the center, heads face outward. Typical CMC values range from 10 to the negative 5 molar to 10 to the negative 2 molar, depending on the surfactant structure. What types of surfactants do we use in droplet microfluidics? Ionic surfactants have charged head groups. Examples include sodium dodecyl sulfate, which is anionic, or acetyl-trimethylammonium bromide, which is cationic. Non-ionic surfactants have uncharged but polar head groups, such as polyethylene glycol chains. Span and tween series are common examples. Fluorosurfactants are specially designed for fluorinated oil systems. They have fluorinated tails that are compatible with fluorinated oils and are widely used in droplet microfluidics. Block copolymer surfactants consist of multiple blocks with different properties, allowing fine-tuning of interfacial behavior and droplet stability. Let's explore the mechanism by which surfactants stabilize droplets. Here's an important question. When two droplets approach each other, why don't they immediately merge together? The answer lies in the surfactant layers. As two droplets approach, the surfactant monolayers on their surfaces create repulsive forces. As droplets approach, their surfactant layers compress and create steric repulsion. The surfactant heads repel each other, preventing coalescence. This is called steric stabilization. The physical presence of the surfactant layer acts as a mechanical barrier. For ionic surfactants, we also have electrostatic stabilization. Like charges on droplet surfaces repel each other. There's also the Marangoni effect. If the interface is deformed, surfactant concentration gradients create interfacial tension gradients that restore the spherical shape. Let's discuss the different geometries used to generate droplets in microfluidic channels. The T-junction is the simplest geometry. The dispersed phase enters perpendicular to the continuous phase channel. Flow focusing uses two side channels of continuous phase that symmetrically compress the dispersed phase. Co-flow geometry involves coaxial injection, where the dispersed phase flows concentrically inside the continuous phase. Here are the three main geometries: T-junction at top, flow focusing in middle, and co-flow at bottom. Each has advantages for different applications. The physics of droplet formation is governed by dimensionless numbers that capture the balance of forces. The capillary number represents the ratio of viscous forces to interfacial tension forces. Capillary number equals mu v over gamma, where mu is viscosity, v is velocity, and gamma is interfacial tension. At low capillary numbers, interfacial tension dominates and droplets are nearly spherical. At high capillary numbers, viscous forces dominate, and droplets become elongated or even form jets. The Weber number compares inertial forces to interfacial tension. Weber number equals RHO v squared L over gamma, where rho is density and L is a characteristic length. The Reynolds number compares inertial to viscous forces. Reynolds number equals RO VL over mu. In microfluidics, Reynolds numbers are typically very low, indicating laminar flow. An advanced concept is interfacial rheology, which describes the mechanical properties of surfactant-laden interfaces. When surfactants adsorb at an interface, they create a layer with both viscous and elastic properties. The interfacial dilational modulus measures the interface's resistance to changes in area. E equals the derivative of gamma with respect to the natural log of area A. The interfacial shear modulus measures resistance to shape distortions without area change. These rheological properties are crucial for understanding how droplets deform under flow and how stable they are over time. Let's explore some exciting applications of droplet microfluidics in various fields. First, high-throughput screening. We can encapsulate single cells or molecules in droplets and screen millions of conditions rapidly for drug discovery or enzyme evolution. Second, digital PCR. By partitioning samples into thousands of droplets, we achieve absolute quantification of nucleic acids with unprecedented sensitivity. Third, single-cell analysis. Each droplet becomes an isolated reactor for studying individual cell behavior, transcriptomics, or proteomics. Fourth, controlled nanoparticle synthesis. Droplets provide uniform reaction conditions, yielding monodispersed nanoparticles with precise size control. Fifth, emulsion formulation for food, pharmaceutical, and cosmetic industries where droplet size distribution is critical. Here are the 5 major application areas. Each leverages the unique advantages of droplet microfluidics: isolation, control, and throughput. Despite the tremendous potential, there are significant challenges we must address. Challenge 1. Many surfactants are incompatible with biological samples. They can denature proteins, lyse cells, or interfere with biochemical reactions. Challenge 2. Maintaining droplet stability over extended periods. Ostwald ripening, where molecules diffuse between droplets through the continuous phase, can change droplet composition. Challenge 3. Preventing nonspecific adsorption of biomolecules to the interface, which can deplete reagents and affect reaction kinetics. Challenge 4. Achieving controlled droplet fusion and fission on demand for complex multi-step assays. Challenge 5. Scaling up production and standardizing protocols across different labs and applications. Researchers have developed sophisticated strategies to overcome these challenges. Strategy 1. Designing custom surfactants tailored for specific applications. For example, biocompatible block copolymers that don't interfere with enzymatic reactions. Strategy 2. Using lipid monolayers or bilayers instead of traditional surfactants. These mimic cell membranes and are highly biocompatible. Strategy 3. Pickering emulsions stabilized by colloidal particles at the interface. These provide exceptional stability and can be responsive to external stimuli. Strategy 4. Dynamic modification of interfaces using light, temperature, or electric fields to control droplet behavior in real time. Let me walk you through a quantitative example to solidify understanding. Suppose we have a T-junction with the following parameters. Dispersed phase flow rate Q sub D is 0.5 microliters per minute. Continuous phase flow rate Q sub C is 5 microliters per minute. Interfacial tension gamma is 5 millinewtons per meter. Continuous phase viscosity mu sub C is 10 millipascal seconds. The question is, what is the expected droplet diameter? First, we estimate the droplet generation frequency using empirical correlations. Frequency F approximately equals Q sub C divided by droplet volume. From mass conservation, the dispersed phase flow rate equals the frequency times the volume of dispersed phase per droplet. Q sub D equals F times V droplet dispersed phase. For a T-junction in the squeezing regime, droplet volume scales with the flow rate ratio. Droplet volume approximately equals Q sub D over F, which scales as channel width cubed times 1 plus the flow rate ratio. Assuming spherical droplets, diameter D equals 2 times the cube root of 3 volts droplet over 4 pi. For a typical channel width of 100 micrometers and these flow rates, we get droplets around 80 to 120 micrometers in diameter. Let me give you a real-world analogy to make this concrete. When you make mayonnaise, you're creating an emulsion of oil droplets dispersed in water. This is fundamentally the same physics as droplet microfluidics. The egg yolk contains lecithin, which is a natural surfactant. Lecithin molecules have a hydrophilic head and hydrophobic tails. When you whisk vigorously, you provide mechanical energy to overcome interfacial tension and break the oil into tiny droplets. The lecithin molecules immediately coat the oil-water interface, stabilizing the droplets and preventing coalescence. This creates a stable emulsion that we call mayonnaise. The same principles apply in microfluidic droplet generation, just at much smaller scales with precise control. Let's look ahead at exciting future directions in liquid interfacial engineering. Direction 1. Developing smart responsive interfaces that can change properties on demand in response to pH, temperature, light, or electric fields. Direction 2. Integration with machine learning for real-time optimization of droplet generation and closed-loop control of microfluidic systems. Direction 3. Organ-on-chip platforms where droplets mimic physiological compartments for drug testing and disease modeling. Direction 4. Synthesis of advanced materials with hierarchical structures using droplets as templates. Direction 5. Development of portable, low-cost point-of-care diagnostic devices leveraging droplet microfluidics for resource-limited settings. Let me summarize the key concepts we've covered today. First, immiscible liquids form interfaces that have high interfacial energy due to unfavorable molecular interactions. Interfacial tension quantifies this energy as force per unit length, typically measured in millinewtons per meter. Surfactants are amphiphilic molecules that dramatically reduce interfacial tension by positioning themselves at the interface. Droplet microfluidics leverages engineered interfaces to create, manipulate, and utilize microscopic droplets as isolated reactors. Dimensionless numbers like the capillary number and Weber number predict droplet formation regimes and behavior. Applications span diverse fields, including high-throughput screening, diagnostics, single-cell analysis, and material synthesis. Ongoing challenges in biocompatibility, stability, and scalability are driving innovation in custom surfactant design and interfacial engineering strategies. To conclude, liquid interfacial engineering is a fascinating field that combines fundamental physics and chemistry with cutting-edge applications. By understanding the molecular interactions at interfaces and how to manipulate them with surfactants, we gain powerful control over droplet formation and stability. This enables revolutionary technologies that are transforming biotechnology, diagnostics, drug discovery, and material science. The future holds tremendous possibilities as we develop smarter, more responsive interfaces and integrate microfluidics with other emerging technologies. Thank you for your attention. I hope this lecture has given you a comprehensive understanding of liquid-liquid interfacial engineering for droplet microfluidics.